All right, so we've got a couple of things to do here tonight. First, we want to wrap up this example that I was working on last time, which basically shows one of the applications of exponential growth functions. And then we'll probably have time to start chapter 3, which is where we're going to look at several very advanced integration techniques. And this is going to take quite a while because a lot of the most important techniques that we'll be learning are in this chapter. So anyway, let's get back to this example that I was showing you last time about money. And so we started out by looking at this formula, which represents the future value of the sum of money. So what we're trying to do here is say, imagine that we started with P dollars in our bank account. How much will we have at some point in the future? So the way this formula is written, let me just quickly run over it with you one more time. A equals P 1 plus R over N to the NT power. So this A is the future value of a sum. This is called principal. This is actually the amount of money that you started out with. R is the rate of interest. And as you're probably aware, the rate of interest is normally quoted as so much per year. It's a percentage of some kind. For example, if the local bank pays 3% per year on your savings account, then you would write that in as 0.03, which represents 3% per year. And then T is time. And that's normally measured in years. And then this is the interesting one. N is the so-called compounding frequency. And it does appear twice in this formula. And so what is that all about? Well, in other words, if the interest is credited to your account more than once a year, which is pretty normal, it's very rare that interest is only paid once a year. So again, with that example of your local savings account, if it's 3%, or that's the rate that's quoted to you, that's an annual rate. Normally in practice, what happens is, in the United States at least, interest is actually paid out every single day. So in other words, you're getting 1/365th of 3% every day that you leave your money in the bank. In this example here, we're assuming that interest is paid out 4 times a year, and that is referred to as quarterly compounding, meaning that 4 times a year you're going to get paid interest, and it'll be a proportionate amount of the yearly total. So for 3% per year with quarterly compounding, that means you'll be paid 0.75% every quarter. Now, you might not think it makes any real difference how often the interest is paid to you, but in reality, it turns out that the more often the interest is paid, the more interest you'll actually earn. So that's very helpful if you're lending or investing your money. But on the other hand, if you're the borrower who's paying interest, that's not such good news because it means that you're paying more interest. Anyway, so we have a quick example here. Imagine that we have $10,000 being borrowed for 3 years with an annual rate of 6% compounded monthly. So when you see those words, that means that you're actually going to pay interest, not 6% once a year. You will pay 0.5% every month. So that's what that wording is meant to tell us. 0.5% every month, as opposed to 6% every year. So the question is, how much interest will this actually cost you? When you pay the loan back, you're obviously paying back the full principal of $10,000 plus some amount of interest. That's what we're trying to figure out. So when you're planning your, your finances, it's important to take this into account. I mean, imagine you're using this money to buy a used car. It's very important for you to keep in mind how much interest this is actually going to cost you. So anyway, here's the variables that we'll need. $10,000 is our principal. The amount borrowed is our principal. The annual rate of interest is 6%, expressed as a decimal. It's a 3-year loan, and the compounded frequency is monthly, meaning that 12 times a year will be charged 0.5% worth of interest. So if you plug these numbers into our formula, and by the way, when you calculate the future value, in this case, as a borrower, what you're actually doing is figuring out how much we'll actually pay back to the bank. If you're saving, well, then clearly this means how much money will you have in the bank at the end of the 3 years. But since you're borrowing, this is basically telling us how much you'll end up paying over those 3 years. So if you plug in the numbers, you can see that algebraically, this simplifies very nicely to 1 plus 0.5% right here. And here, the number 36 means that you're actually paying 36 monthly payments as opposed to 3 yearly payments. So this ends up being $11,966.81. Now, because you started out with $10,000, it should be pretty clear that the you ended up paying $1,966.81 in interest. Okay, so in other words, if you the future value or the total repaid is $11,966.81, but you originally borrowed the $10,000. Whatever's left over must be the interest. All right. So there's several other examples in here that you could work through on your own. I think I'd like to skip over this and get to the important detail here. And this is what the tie-in is with our exponential growth rate. So if you can imagine that we keep increasing the compounding frequency n. In other words, imagine if instead of having monthly compounding, we have daily compounding, and then we can keep pushing it even further. Imagine if the compounding takes place every hour or every minute or every second. There comes a point when there's a limit to how far we can push this. So what we're going to do here is take the limit of a as n goes to infinity. Now, of course, if n goes to infinity, this term is getting very, very close to 0, and this term is getting very close to infinity. We end up with e to the RT power. Actually, it's p times e to the RT power. Aha, see, so in other words, when we reach the limit of how often we can compound a frequency, or think of it as infinitely many compounding periods, per period of time, then we reach the limiting case of how much interest we could either earn or pay, which is known as continuous compounding. Okay, and you can see this formula exactly matches our exponential growth formula that we saw earlier. That's what we've been building up to. In other words, when we have what's called continuous compounding, then the balance in our bank account will grow at an exponential rate, or else we can think of this as the amount we pay back is going to grow at an exponential rate. Okay, so imagine that we had a situation where an investor puts $1,000 in a 1-year account that pays an interest rate of 4% per year, but the rate is compounded continuously, rather. And so this is the final result. So you can see here that the future value is $1,040.81 and some change. So what this is telling us is that under these circumstances, the interest that we're earning reaches its maximum possible value at 81.0774 cents. Had we used this less frequent, let's say instead it had been n equals 12 like we saw before, let's just see how much of a difference that would have made. Just out of curiosity. And this is only for 1 year. All right, so hold on one second. Let me get out my calculator. Okay, so in this case, you would have ended up with $1,040 and 74 cents. So you can see it's kind of disappointing, actually, when you think about it. The difference between your interest being compounded every month versus continuously only ended up bringing us an extra 7 cents. Now, if we had a larger amount of money to start with, or if we left the money in the bank for a much longer period of time, then the difference between the two would start to be quite considerable. But in a short period of time, the two are very, very close to each other. And in fact, what you could even do is draw a chart which shows the relationship between the amount of interest that we're earning and the compounding frequency. Hold on. And it would look something like this. So you can see it's increasing at a decreasing rate, and this would be the limiting case, which we only reach when n approaches infinity. Okay, so this is what the relationship looks like. So there's if I keep increasing the compounding frequency, the amount of interest at first grows fairly quickly, then it levels off, and it converges to this upper limit, which is what we reach when we have continuous compounding, rather. So that's a real world example of exponential growth. If you were to turn around and draw another graph showing the balance in your bank account with continuous compounding, it's going to look something like this. Okay, so in other words, the balance in your account, at first it grows fairly quickly, but then after a while it starts to really accelerate, because what starts happening is after a while you're earning interest on a progressively larger balance, and so it starts to really grow quickly down the road. And so it's kind of a reminder why it's good to start saving young, because the amount of money you can save can grow quite considerably if there's enough time involved. All right, well, anyway, now what about the exponential decay example? For this one, we turn back to physics and we talk, and remember, oh, by the way, I just want to remind everyone that this is the formula for exponential growth, or sometimes it's called continuous growth. And this is the formula for exponential decay. And the only difference is the sign of the exponent, positive, negative. So they're inverses of each other. So here's a quick example from physics. Imagine that you have a radioactive element that decays at the rate of 5% per day. In other words, that radioactive element is converted into lead. And then we start with 100 grams of this element in our sample. How much will still be radioactive after 10 days? So we plug in all these numbers. You can see, wow, that's pretty fast. That's a lot of decay. Because what's happening is that the amount of radioactivity that's your dependent variable, and this would be time, it's falling off at a very rapid rate. Yeah, I can't let it actually touch the axis because that is an asymptote to this function. In fact, the vertical and the horizontal axis are both asymptotes in this case. And so it falls off very quickly at first, and then it starts to level off. So after 10 days, we're down to 6.0653 grams. But, 5% a day is quite a bit. That's why this is happening. Now, by the way, here's a fun little side note. Suppose you want to know if, let's say, the balance in your bank account is growing at an exponential rate because you're getting continuous compounding, and you want to know roughly how long it'll take to double your money. you can use this formula. You have the natural log of 2 over k, where k is the exponential growth rate. So here, for example, is an example from biology. Imagine yourself with 500 fish in a pond. After 6 months, there's 1,000 fish. At what point will the population reach 10,000? Now, we're assuming exponential growth, of course. So if time is measured in years, k is now the annual growth rate. So 0.5, so what we're basically saying is that the population initially was 1/2 of what it is now at 6 months later. So what this is saying is that the growth rate over those first 6 months, k, is 138.6%. Not bad. And then, in order to figure out when we'll reach 10,000, we're going to have this original formula. Now, 10,000 is the target. 500 is the initial amount of fish. K is the growth rate, 138.6% per year. And T is the time that elapses. So now what I can do is take the log of both sides of the equation. So I've got log 20 equals 1.386T. And now this is so easy because all I have to do is divide both sides by 1.386. And so I'm left with approximately 2 years. Okay, because the population of the fish is growing so quickly, it'll only take about 2 years to go from, where is that? 500 to 10,000. Okay. And then the opposite of that, the half-life, we can do the same thing with that same formula. If the variable decays exponentially, the time that it takes to cut its value in half is the natural log of 2 over k. So here's an example everybody's familiar with. The half-life of isotope carbon-14 is 5730 years. So in other words, after 5,730 years, half of the carbon-14 molecule in a substance has reverted to the non-radioactive isotope nitrogen-14. And it decays at an exponential rate. Now, this is all well-known, well-documented, and this is why it's possible to date things with carbon-14, because it's completely predictable. So if we have some substance containing 100 grams of carbon-14, how much will be left in 50 years? Okay, so the decay, the half-life is 5730. We set that equal to log 2 over k. And so you can see not much is left, 100 down to 0.000121 after 50 years. So, oh, I'm sorry. This is the growth rate. What am I saying? This is the decay rate. This is not the amount that's left. This is the decay rate. Now we plug this back into the original formula. And at that rate, wow, that's pretty slow. But remember, we're looking at thousands of years here with carbon-14. It's not a quick process at all. It's not like the way radioactive isotopes decay. This is a very long, drawn-out process. So according to this, after 50 years, we're only down to 99.4 grams. So if we started out with an artifact that had 100 grams of carbon-14, now it only has 10 grams left. How old is the artifact? And this is exactly how this is done in practice. So we use the exponential decay formula. We have that decay rate of 0.000121. We're solving for t. We take the natural log of both sides. And wow, 19,000 years. That's going back pretty far. I don't know, is that the Stone Age maybe, or the Bronze Age? I'm not sure. I'd have to look it up. But anyway, so the half-life and the exponential growth in a bank balance are both examples of exponential growth and decay. So now, anyway, we're done with that. So now we can start chapter 3, where, like I said, we're going to be spending a lot of time looking at integration, and we're going to be confronted with some very complex situations. So ultimately, what we're going to try to have to do is first learn the techniques, but then we have to come up with a way of identifying which technique makes the most sense in each case. And that often is the biggest challenge. Just take a look at it and try and see if you can figure out which technique makes the most sense. And of course, if you guess wrong, then you'll find yourself just turning the function into something even messier than what you have. So what's going to come up first in this chapter 3 is a very important technique called integration by parts. Okay, now you can see there's others too. The next two involve trig integrals. And before we get to that point, we will quickly review trigonometry or trig functions. And then, of course, you can see we also have partial fractions. So the trig functions we'll get to fairly soon, but for now, we want to focus our attention on integration by parts. What exactly is this all about? Well, the integration by parts is based on the product rule for derivatives. So let's just quickly review this. Suppose you have some function h of x, which is the product of two other functions, f of x and g of x. What if I take the derivative of h of x? What does that give me? All right, so you probably remember the rule, which I just want to mention here that there's different ways of expressing it. This is the way that I memorized it when I first started out in calculus. And so what you've got is the first times the derivative of the second plus the second times the derivative of the first, or h prime of x equals f of x g prime of x plus g of x f prime of x. So if you had, for example, something like this, the derivative could be written in the following way. Uh, Actually, I'll tell you what, let me do it to be consistent. Let me call that h of x, just so we can see how it follows along with this rule. So that what that means then is that f of x is x squared. F prime of x is 2x. G of x would be the x plus 3. And therefore, g prime of x is just 1. So now I plug them in. Here's my f of x. Here's g prime of x. Here's g of x. And here's f prime of x. Now you could simplify it too if you want. You've got x squared plus, if you distribute this 2x over x plus 3, you'll have 2x squared plus 6x. And that's your final result. Okay, now this actually is the starting point for integration by parts, because what you're effectively doing is reversing this process with integration by parts. In other words, it's like, imagine you're confronted with the integral of this expression, and you're trying to work it back to the original h. So the question is, how do you do that? And how do you know when it's time to use this technique? All right, well, first let's figure out why the rule is what it is. We use this as our starting point. Now we're going to integrate both sides of this equation with respect to x. So we have h prime of x dx, and you can see what we've done here. We simply integrated the product rule. Let me just repeat it up here. Now, so I just literally just integrated both sides. And so, let's see, this, when we integrate it, we don't have the actual functional form yet, but the integral of h prime of x is just h of x. And we already know that by definition, this is equal to f of x, g of x. So this is what we're after right here. And then the right-hand side hasn't changed. Okay. Now I'm going to do a little algebra. And you might recall that one of the basic properties of integrals is that the integral of a sum equals the sum of the integrals. Just a quick reminder. So that's where the next step comes from. So you notice what I've done here. We don't need to worry about h of x anymore. Here I've just broke this up into two individual integrals. And now the next part is to rearrange it. Now this is what we're solving for. So what I'm going to do is subtract this expression from both sides. So now you've got the integral of f of x g prime of x dx equals the product of f of x and g of x minus this integral over here. So in other words, literally nothing's changed here. We just rearranged it to solve for the integral of f of x g prime of x dx. Now we're going to change the notation slightly just to make it a little easier to remember this. Okay, so that's the only motivation for this next part. This is a lot to remember. All of this notation. What is traditionally done here is that we replace the f of x with u and the g of x with v. Okay. If that's the case, then du dx is f prime of x, or du means f prime of x dx. And if we let v take the place of g of x, we end up with the same thing. dv is simply equal to g prime of x dx. So this expression can be simplified in the following way. This is u. All of this is dv. This is u, this is v. This is v. And this is du. So this is now the statement of the integration by parts rule. Okay. So when you see that, you have to recognize, you immediately think integration by parts. Integral of u dv equals uv minus integral v du. Now, we don't really, I guess it's one of those things where I guess technically you should memorize it so that you'll recognize it when you see it. Especially because, like I said, when you see a bunch of integrals, this would help you recognize that you're looking at a case that requires integration by parts. So if you're making up a study list of some kind, this probably should get on there somewhere because this is awfully important. Now, when you see the next example, you'll say, ah, I see why this is so important. Let's say you run into this case. Now, clearly, this is not a job for u substitution because no matter what you set u equal to, you're not going to find a du. It isn't going to work. So that means clearly that is not the right technique. Now, here's the big question. Is it a job for integration by parts. So remember, you need four things. You need to worry about u, du, v, and dv. And remember that the whole technique is based on solving for u, the integral of u dv. So if you're going to use this technique, what you have to do is make a decision. Which of these terms is going to be your u, and which one is going to be your dv? And keep in mind that whatever you choose for dv, this has to be part of it, okay? If you guess wrong, you'll know it right away because it starts to become even messier than what you started out with. The whole point of this is to simplify what you have into something more manageable. So in this case, why don't we try this? U is x. Du is dx. This implies that dv is this part. Now, here's what gets a little awkward. That means we have to integrate dv to come up with the correct value for v. So what do we have here? By the way, when we're using this approach, we don't need to bother with the constants until the very end. In other words, you don't have to continuously write them because you'll end up consolidating them all at the end anyway. So in other words, you notice how I wrote this as integral sine x dx is negative cosine x. Normally there'd be a plus c there, but we don't have to worry about it here. Now, I do want to point out, by the way, that in our book, which you seem to have forgotten to open, let me go get it for you. In the back, you're going to find a nice little table of integrals and derivatives, which all calculus books do. We just have to find it. Especially with some of the functions like the trig functions, it's easy to forget some of these important results. So let's do this. Let's go find their charts. Oh, they're way at the end somewhere. All right, so we're looking at the tables of integrals. And, you know, they're in here. Don't worry about it. Here we go. Right there. The integral of sine u du is negative cosine u plus c. So, yes, there it is. Okay, so therefore, the v that we need is right here. Okay, great. And again, don't worry about the c's until the end. Well, don't forget it, but well, we won't need the individual c's because we don't know what they are anyway without further information. So we're just at the end, we'll lump them all together into one big constant. So I've got all four of them. Now it's just a question of plugging them in here. All right. So what do we end up with? So let's see. Let me just quickly summarize these one more time. U is, oh, here it is. U is x. Du is dx. dv is sine x dx. And v is negative cosine x. Oh, here it is. So here I was just showing you where that came from. Now we've got to plug them in. Okay, here we go. So the rule again is integral of u dv is uv minus integral of v du. Right, oh, here it is. The expression we started out with was x sine x dx. And again, a quick reminder, u is x, du is dx. dv is negative cosine x. No, it's sorry. I got it backwards. V is sine x dx. No, sorry. Hold on. Let me just double check. I was right the first time. It's minus cosine x. And then this is the sine x dx. Perfect. Now we just plug them in. Okay. So here we have u, v, minus integral v du. So on the left-hand side, we simply have minus x cosine x. But here, you may want to consult with the table. And if you do, the integral of cosine u du is simply sine u du, sine u. And now here for the first time, you're going to see the constant. By the way, I just want to quickly remind you that as far as the derivatives go, the derivative of sine x is the cosine of x. The derivative of the cosine is negative the sine. And that's why the integral of cosine x dx is negative sine x. And the integral of sine x, oops, forgot the x, is cosine x. Just a quick reminder. Okay, and the chart is right here anyway. Interval sine u is, oh, geez, I wrote them backwards. Sorry, hold on. That's better. All right, that's good. Okay. Also, there's a derivative table here anyway. A is the integrals. And so if we forgot those, or if we forgot these, they're down here somewhere. God, look at that list. They get really terrifying at the end there, don't they? If you notice too, the list of integrals is much, much longer than for the derivatives. God, look at that. By comparison, these are a piece of cake. Derivative of sine x is the cosine of x, and derivative of cosine x is negative sine x right there. Okay. Yeah, I mean, look at that. All right. So we're done. Okay, this is the final answer right here. And again, how would you know just by looking at a problem like this that it might be at least the integration by parts, because it's a product and at least one of the functions is very complex. Like it's not x times x cubed or something like that. In other words, it's two fairly messy expressions multiplied together. And also, what happens? What if you got this backwards? Just for the fun of it, why don't we see what would have happened if we got it backwards? If we recognized that, yeah, now it mentions it in here, like if you got it backwards, you would have had a problem on your hands. But let's just quickly see what this would have led to. So the original problem was x sine x. And we decided to go with u as x. All right, fine. What if we'd done something like this. U is sine x. Du is cosine x, dx. dv would have been x dx. And then v would have been. So when you plugged in all these numbers, you would have gotten sine x times x squared over 2 minus the integral of x squared over 2 cosine x dx. And I think you'll agree that that's actually a lot worse than what we started out with. Okay, in other words, it didn't simplify anything. If anything, it moved us into a more messy expression. So that would be a sign that these substitutions were not the best choice. Okay, the whole idea of this is to simplify what we're trying to do. And in the beginning, it'll be easy to make mistakes like that. But once you see that you're getting yourself into a much more complicated scenario, that means you should go back and change the choices that you made for u and dv. Okay, because chances are you got them backwards. Now, here is one. Now, this one is really a very challenging one, I must say, but maybe not. We'll see. Well, let's try this. First, let's assume that we're going to use integration by parts. The last time, it seemed like the u was the simpler one. Is that going to happen again? Let's see. By choosing u to be x, all of the rest of this has to be dv. We don't have any control over that. So as all du is therefore dx, I could put this over here. Maybe this won't be so bad. What do we do with this one? Now, this by itself can be approached with u substitution. All right, this is something that's not that difficult. Let's go down here and try it. So if all we have is this piece, v equals e to the 2x dx. So remember that e to the u du is simply e to the u plus c. Now here we got to be a little careful. This u is not the same as the one we had just a minute ago. In other words, this u, if we're going to use u substitution here, just remember it's a different u. So what we could do is say, all right, if we let u be the 2x, du is 2x dx. We don't have that. We have dx though. So let's do this. Oh, wait a minute. Oh no, we have a problem here. This does, oh, we're missing. No. Now we really do have a problem. Oh no, sorry, it's my fault. I copied this wrong. No, we're good. I just wrote, here we go. This should have been 2. That's better. Now we're getting somewhere. All right, great. Oops. 2 dx. That's okay. That means that, and then this is the part that we don't have, so let's apply it. Okay, so I multiplied the dx by 2, and I multiplied the outside by half so that I haven't changed anything. And now what I've actually got here is 1/2 integral e to the u du, 1/2 e to the 2x plus c. Because this is clearly e to the u. E to the u is 2x. Now, we bring this back. And by the way, again, we don't need to worry about the constant just yet. So we come back here. And that means that dv now we can make the substitutions, okay? All right. So remember, integral u dv is uv minus integral v du. All right, so I'll have to move that onto the next slide. So based on what we just discovered, we determined that okay. And so what we're aiming for okay. So u here, v is 1/2 e to the 2x. Okay. Now we just got through showing that the integral of e to the 2x is 1/2 e to the 2x. And then we can worry about our c. So ultimately, what do we have here? 1/2 x e to the 2x minus 1/4 e to the 2x. Let's see, or if you want to consolidate them, you can. So that is it. That's, yeah. Okay. So ooh, that was a lot of work. All right, so that's a lot to absorb for one night. So I'll tell you what, why don't we stop it right here? And then next time we'll start by practicing with this integration by parts. We're going to do several examples, and I mean quite a few examples, so that we can really get the hang of this, because you can see it can be a real a very complex process, let's put it that way. So here's what we'll do. We'll stop here. I don't want to go into anything new just yet until we've had a chance to really practice like crazy with this. So next time we'll just dive into these problems and do several of them until we really start to get pretty good at it. And then what comes after this, like I said, is the trig functions, the trig integrals rather. So before we do that, I want to have a quick review of the trig functions, and then we'll dive into those techniques. And then we'll save the partial fractions until the end. All right, the end of the chapter, that is. Okay. All right. So I guess we'll call it a night, and I'll see you next time.